Okay, so topic 8 is on static electricity. Static meaning non-moving. In topic 9, we'll look at dynamic of electricity and moving. So statics, it's often called. Okay, and it has to do with properties of matter. Okay, and mass is an inherent property of elementary particles. So you could have a proton. You could have an electron. Okay, and each of these, and there's also neutrons and other particles as well, but each of these have a certain mass, and that's an inherent property. Okay, those are inherent properties. So what is the mass of a proton? What is the mass of an electron? Well, you could look those up in your reference table, and the mass of a proton is 1.6 times 10 to the minus 27 kilograms. Pretty small, right? But the electron's mass is 9.1 times 10 to the minus 31. Checking. Kilograms. Much less. 4 orders of magnitude less. So charge is an inherent property of these. If you have 2 protons, the mass would be 2 times 1.6 times 10 to the minus 27 kilograms. Likely the same thing, 2 electrons, 2 times 9.1 times 10 to the minus 31 kilograms. Okay. Charge is also an inherent property. A neutron has a charge, no charge, it's neutral. A proton is what we call a positive charge. An electron has what we call a negative charge. So for mass, mass has the property of attraction. Masses attract. Okay? Charge is an inherent property that can cause attraction or repulsion depending on the situation. So this we call 2 flavors. And this one, for mass, is only 1 flavor. It's always attraction. But for these elementary particles with charge, it can be both attraction or repulsion. But it's also an inherent property, and you could take the charge of an electron, or charge of a proton, and the charge of 1 proton has a charge of positive 1.6 times 10 to the minus 19 Cs, which is coulombs, which we'll define later. And for electrons, should have made this black. Hold on. For electrons, the charge is minus 1.6 times 10 to the minus 19 coulombs. And if we have 2 electrons, it has double that charge. 2 protons, double that one. Okay? So it's easy to understand how objects can acquire charge with our modern atomic model, right? Because we have a positive nucleus made up of protons and neutrons, and then the electrons are in orbit. The negative electrons are in orbit around it, like so, in different orbitals. The stuff is made out of this positively charged nucleus surrounded by negative electrons. The interaction between them is what keeps the electrons in orbit. So there's an attraction between the positive nucleus and the electrons. But they're moving, so they're moving around in orbital motion. Okay, so if an outside force is applied to these electrons, they can leave their parent atom and go somewhere else. So if we were to move this one out and away, then this is left with an overall positive charge, isn't it? Because before we had 4 positives and 4 negatives. Now we have 4 positives and 3 negatives. That leaves an overall positive charge. So by removing these electrons, we can gain a charge. Or we can add electrons. If we got it, it had to take it from somewhere else, but if we add it, and then now we have an overall negative charge. Okay? So charge, we need 2 ways for this model to work, 2 things. Okay? And these 2 points are that the 2 rules are 1, charge is quantized, and 2, charge is conserved. What do these things mean, charge is quantized? Well, the first rule means that there's a smallest piece. Where it can't be divided any further. So you can't break it down any further past that charge. The smallest piece, for our purposes, is a charge on the electron, which is identical in magnitude to the charge on a proton, just opposite charge. We're going to denote this as E, okay? The symbol for the charge of 1 electron. So let's think of this quantization thing. You can't, there's the smallest piece of charge, which happens to be that 1.6 times 10 to the minus 19 coulombs. And you can't divide that up any further. You could have 2 of those, which would be 2 times 1.6 times 10 to the minus 19. You could have 3 of those. You could have 3 million of them, but it has to be an integer multiple, okay? So we write this rule where the overall charge, which we call Q, equals plus or minus n times E, where E is the charge of an electron, and N is an integer value. 1, 2, 3, 10 billion. Okay? And that means that a good example of this is like of this division of quantization is that if you go to a Coke machine, right, and you want to purchase a soda, and you put in $1.25, or let's say $1.50, be more realistic nowadays, and a soda comes out, 16 ounces. Now, let's say you only want to purchase an 8-ounce soda. You put in 75 cents, and the machine just does nothing. It does not give you half a soda, okay? Because the smallest fundamental unit of soda is one soda. You can have 2 sodas or 3 sodas from the machine or 4 sodas, but you can't buy 4.5 sodas from the machine, okay? So it's quantized. It's integer values of that. And the same thing works with charge. So if we were to take all the electrons in your pen that you're holding, it has billions upon billions, quadrillions of electrons in it. All those electrons that are in it, if you just took the electrons away without the protons, they would have a charge of Q equals billions upon quadrillions times 1.6 times 10 to the minus 19 coulombs. Okay? They would not have a charge of a billion times quadrillion 0.3 times 10 to the minus 19. It has to be an integer value, this n, that you're multiplying. There's the smallest piece. You can put a bunch of smallest pieces together to come up with larger charge. But you can't break those smallest pieces up. And then the second rule, charge is conserved. Well, you're familiar with this because we've been conserving things in this class a lot. The total amount of charge before is equal to the total amount of charge after for electrical interactions. In equation form, if you sum up all your Q's initially, they're going to equal the sum of the Q's finally. So you might take one object and another object, and some electrons might be transferred from the one object to the other object. So now the other object has a net negative and the other has a net positive, but overall, that net charge before is equal to the net charge afterwards. Okay. So that's actually on the model. It's 8.1a. Where can we put A? Let's see. We'll start it here with charge as an inherent property. Okay? And now 8.1b, we're going to do this in 2 parts, so another video will be C and D because this is long, is conductors and insulators. And this has to do with the electrons floating about on the surface of things. Okay. So, all atoms are ideally neutral. Okay? So you have a positive nucleus and maybe some neutrons around in that nucleus. And if there's 3 protons, there's 3 electrons going around, right? Like something like that. Electrons combine with the nucleus so that the positive and the negative charges add to zero. Of course, atoms don't have to stay neutral. They can lose electrons and gain electrons. Okay? So we can see that they can become positively charged particles or negatively charged particles, or positively charged items and negatively charged items, not just for certain atoms and certain particles. Atoms don't have to stay neutral. They can add up. The different flavors of atoms have different respect with how they treat these electrons. Some of them hold them very closely in, okay? And others have some that are close in and some that are, bring this back to neutral, and some that are out, that are more free to roam. These outer electrons out here, which you'll learn much more about in chemistry next year, are called valence electrons. So it's all based on these orbitals. See, they could fill, you have s orbitals, p orbitals, d orbitals, f orbitals, okay, just by nomenclature. And if you have a filled sublevel, or a filled sublevel, then the next electrons that in a partially filled sublevel, or partially filled level, are the ones that we consider. You can have a filled level, and then the ones in the outer partially filled level are called the valence electrons. And those are the ones that are available for interactions with other atoms, usually. It's harder to get down to the ones from the filled orbitals. So different atoms, or different types of atoms have different pulls and different works on these outer electrons. And some hold on to them very tightly, others loosely, which brings up a new term which we'll call electronegativity. And the electronegativity of an atom is its ability to hold electrons. High electronegativity, high ability to hold electrons. Low electronegativity, opposite. Low ability to hold electrons. Okay? So the various atoms exhibit the spectrum of behavior based on subtle differences in electronegativity. Okay? And so, but most of the times we lump these into two basic things based on their electronegativity. We say, okay, if it has a high electronegativity, we call it an insulator. If it has a low electronegativity, we call it a conductor. Okay, but there's a wide range. Some conductors are more prone to hold on to their electrons than others. Some insulators are more prone to hold on to their electrons than other insulators. So they're lumped into this dichotomy, but they're as insulators and conductors, but there's a range. So a conductor is a material whose constituent atoms have loose valence electrons. Okay? So these have loose valence electrons. They're able to move around. Okay, it's actually why a metal sparkles and stuff, because those valence electrons are moving around. That's the electrons moving. It gives it the shiny sparkle of a metal. And we consider these free electrons, they're sometimes called. They can move however they want in the material. Not so much with the insulators, okay? With insulators, they're hold on to their electrons. Okay, keep more in place. But they're able to shift some in and around, okay? So metals are good conductors, and glass and plastic are good insulators. And we'll see demonstrations of this in class, so you'll get at it there. Here's a model of conductors and insulators that we're going to use in charging and things like that, okay? So in this sense, we'll take, just you've seen these things probably popping up on here, but if we look at the well depth here, this well depth model, this is the representation of a conductor, and this will be our representation of an insulator. They both have the positive center representing the nucleus, the positive nucleus of atoms. And then the valence electrons that are around in the wells, like so. The conductor has a shallow well compared to the insulator. The insulator has a deep well. That means the electrons in the conductor are able to get out more freely and go around the surface, bounce around, kick another one out, things like that, and move around and create ionization trails and make things sparkle, make electricity flow if it's given a direction and a reason to flow, and things like that. Where these, it's harder to get out of that, isn't it? It's harder to get out of that well. And for some insulators, oh, was that the one I wanted? Yeah, I guess so. I wanted one with deeper wells. It doesn't really look that much deeper. But you could have deeper wells, I mean a stronger amount of an insulator. Okay, so that's part 1 to